I'd like to start drilling into the unknowability of spacetime.
Okay.
So you have some theorems on this, and it says something, again, correct me if I'm incorrect, roughly like from your spot, from your local spot, you'll never be able to determine the global structure of spacetime. Now, said the way that I said it, that sounds trivially true about anything. From your local spot, you'll never be able to know some global structure. Well, you don't have access to the global from your local.
Mm-hmm.
So what have I said that's incorrect? What is your theorem and what are the implications?
Yeah, everything you've said is correct, but I would just go further. So it's not just that from this event, I can't know what the global structure of space-time is like. It's not just that from that event I can't know. It's that it doesn't matter where in the universe one finds oneself, whether that's in the past, present, future, here, there, everywhere. It doesn't matter. Suppose that you give me all of that data. Suppose that you have an eyeball everywhere in the universe. Everywhere in the universe, there's an eyeball there.
Okay.
And then suppose that you're somehow able to relay the information that the eyeball is seeing at every event, everywhere, not just where you are, but literally everywhere and every when too. This is not just in the past and present. This is every possible event, even in the future. Now you give me all of that data. I'm going to go back in my workshop and I'm going to come up with a model that's going to reproduce all of that data, but it's going to be completely different from the model of the universe that we started with. Whatever structure that you may suppose that our universe has, I'm going to find one that's completely different from that, but that reproduces all of that data. Moreover, that was conjectured back in the 70s that was possible by David Malamut. It was not proven until 2009.
By yours truly.
Yeah. So I was very fortunate. David helped a lot because he gave in his paper a sketch of a proof, and I used that sketch. I built upon it. But one thing I want to emphasize that I don't think many people realize is that I went way beyond what David had conjectured.
Right.
David said nothing about local structure. So he conjectured that if you give me a space-time, well, I'll be able to come up with this nemesis space-time that reproduces all of the data, but that is completely different. Now, that's one thing, but it's a completely extra level to say, well, now not only do you just give me the space-time, but you tell me that you want to preserve some kind of local structure. So, for example, if you give me a vacuum solution, maybe you want to preserve the fact that it's a vacuum solution. So I can't just go off and build whatever model I want as the nemesis. I'm now constrained. I have to build a model that is a vacuum solution, or whatever other local property that you could possibly think of. And it turns out that the theorem does go through even under those additional constraints. And so what that does is it closes off a common response, I think, to the work, which is, I think folks think, well, is it, of course, deductively, if you give me some data, it's not going to deductively prove that the universe has to be a certain way. Nobody ever thought that. Science doesn't work like that. Science works on induction, right? Science works in a way where you tell me what the local structure of the universe is like here, and even though I can't observe it over there, I'm just going to kind of extrapolate or do some kind of induction that says, well, the local laws of physics aren't going to be completely different over there. They're going to match what's going on here. So I'm going to do it a little induction. What this extra step, this extra level that I'm talking about with this unknowability theorem is it shuts down any response that says, oh, well, you're not doing an inductive type thing. You're doing a deductive type thing. I want to say, no, I'm telling you to give me all of your data, and I'm allowing you to do any kind of local induction that you want. You're still not going to be able to pin down what the universe is like. The only way to wiggle out of this is to do a global induction, is to start assuming certain global properties about the universe. But that's precisely what's at issue here,
Mhm.
right? The whole point of the theorem is to say we don't have any idea what the global structure is like. So if you start whipping out global properties and saying, well, I can shut down your theorem by, appealing to this global property, I want to say, where does that come from? It's not coming from any empirical data that we've gathered. It's not coming from any sort of like local induction that we're doing. Where that's coming from is just an assumption about the way that you want the universe to be. So it puts the pressure back on the person who wants to say that we can somehow know the global structure.
Are there some inductions or some assumptions that are reasonable, like Occam's razor, to say that this one is more simple than something more bizarre than that you may come up with?
Yeah, that's an interesting question. I mean, maybe you could somehow make that rigorous. I don't know, though. I mean, I don't. There's no natural sense in which there's a property of simplicity that has manifested here that's a useful thing to consider. I mean, I think rather what folks want to use are the properties that we've been talking about. So they might say, well, if you're dealing in globally hyperbolic spacetimes, then you're not going to be able to do this. Or if you are working with spacetimes without holes in some sense, you won't be able to do this. I have a response to that sort of thing. But the simplicity stuff, yeah, I mean that's a type of non-empirical, almost metaphysical type of thing that you're going to have to insert into theory choice to get you to go this direction rather than this direction. I'm not aware of anything along those lines. I'm interested in this sort of thing. I think that probably the most promising approach isn't a metaphysical thing. It's more of assuming that space-time is radically asymmetric. And if it's very asymmetric, then it turns out that local structure is actually equivalent to global structure. And so
Right. Heraclitus, you're speaking of your spacetimes.
Yeah. And so then you have an entry point, because then if I am allowing you to do local inductions, what you can do is you can say, well, I want my local structure to be kind of like a local structure of this model over here, and that will uniquely determine the global structure. So that's one way through. It's a way that I've explored with a co-author, Thomas Barrett, where we're, in a way, it's kind of like arguing. I'm kind of arguing against myself in some way. And that's a trip to write a paper where you're kind of arguing against yourself. But I think it just shows the limits of the theorem. Every theorem has its limits, and so this is going to be one of those. What I would say is that because local structure and global structure come together in context of radically asymmetric spacetimes, you might want to consider weaker types of local structure inductions that you would be able to do that don't qualify. So what I mean by that is, if you said, for example, okay, you can do local inductions, like you can assume various types of standard energy conditions, you can talk about vacuum solutions, you can talk about that sort of thing, well, then the theorem goes through just fine. So it's really that the fact that when I'm proving my theorem, I'm working with the most liberal notion of local property that I can possibly come up with. And when you're dealing with something like a Heraclitus spacetime that's radically asymmetric, that I've just let too many possibilities in, and the local structure actually it turns out to be equivalent to global structure. It shuts the whole thing down.
What is a Heraclitus spacetime?
Yeah, good. So a Heraclitus spacetime is a spacetime where you give me any distinct events in the spacetime, and I claim that if it's Heraclitus, those two events are different in some invariant way. So they have different local structure. And so, Heraclitus is famous for his constant theory of flux, this radical flux that's happening. Everything's always changing. He famously said, you can't step into the same river twice. And so that's the idea here. You can't step into the same river twice means that if you step into the river the first time and you try to do it later on, there's going to be some difference there. It might be the same with respect to some properties, but it's going to be different relative to some others. And so a Heraclitus spacetime is something where, yeah, every event is different from every other.
Okay, so to the keen-eared listener, which is probably the better word than hawk-eared, I said earlier, they may be thinking, well, what is it that you mean by local structure? Isn't the fact that we're on a manifold, doesn't that mean that everywhere already has the same local structure? If everywhere looks like Rn, what is this local structure you keep saying can vary from point to point?
Oh, yeah, that's a great question. If you're just dealing with a manifold, then every point is just like every other, right? It's important that when we're working in GR, we're not working just with the manifold, we're working with additional geometric structures on top of it. In this case, a Lorentzian metric. So it's the Lorentzian metric that's going to be different here rather than here. The Lorentzian metric is telling you what's the geometry like at that point. And so in a Heraclitus spacetime, it's really weird, but each point has its own geometry going on.
Okay, what if someone says, and I'm sure you've heard this, locally every point looks like Minkowski space?
No, that's not true. I think that's a common misunderstanding. Minkowski spacetime is flat. There's no curvature there at all. What I mean by that is that if you look at various types of curvature tensors, like you may be familiar with the Ricci scalar field, on Minkowski spacetime, that's 0 at every point. In an arbitrary spacetime, that's going to be varied over the spacetime. It's going to have curvature associated with it, and that curvature must be preserved by any kind of mapping from one point to another. If you're going to say that these points are the same, then you're going to have some kind of isomorphism from one point to the other that's going to preserve that structure. And so what we do in a Heraclitus spacetime is we look at properties just like this, the curvature properties, and say, there's no 2 points with exactly the same curvature properties.
Some people may object and say, well, okay, if we're going to assume space-time is continuous, sure, we can construct such wildness. Maybe there's something about Zorn's lemma, which we'll get to, that is necessary for these Heraclitus structures. But maybe, space-time, sorry, but maybe space-time is discontinuous, or we don't have a theory of quantum gravity. So we're speculating at something that's sub-Planckian classically, but perhaps we shouldn't. How do you think about all that?
Yeah. Well, it's very common to have, for a variety of mathematical structures, one looks at the symmetries of those structures. One can do that for a set. One can then add some topological structure and look at symmetries of a topological space. One can do the same thing for a manifold structure. So there are all sorts of levels of structure that one has in mathematics, and at all of those levels of structure, what you want to do is look at the symmetries there. And what we're doing is basically drawing attention to the fact that unlike a manifold, say, where each point is just like any other, in generic spacetimes, you just don't have symmetries, and you don't have symmetries in a global sense, and you don't have symmetries in a local sense either. And so what that means is that these structures without symmetries are very common, not just within GR, but it's basically any kind of mathematical object that you're going to want to look at. You start looking at the space of all of the objects. It's almost certainly going to be the case that generically, a randomly picked arbitrary example is not going to have any symmetries. So that would be my response, is that this assumption is not some kind of special condition that happens only in very special cases. We think that probably almost every general relativistic spacetime is Heraclitus. It's just that these are very hard to write down, and so you open up a textbook.
Right,
you're not going to see these. You'll never see these in a textbook, because in order for you to study these things, you're going to need symmetries to make them simple.
So let me ask you this: is it the case then that we can say that approximately Heraclitus becomes FLRW or something like that in order to infer the Big Bang, because the Big Bang models have so many symmetries to them? So I'm not understanding, if the universe actually is Heraclitus,
Yeah.
then does that put doubt into something as profound, important, seemingly fundamental as the Big Bang? How do you see that?
Yeah. It's a great question because I think what's going on is that there are different levels of scale involved. I mean, the Heraclitus point is that if you're really zooming in on each point and looking at its very particular curvature properties, that you're never going to find any two points with exactly those curvature properties. When you're dealing with something like FLRW models, you're zooming way out. You might talk about maybe that there are approximate symmetries in that sense. And there have been some philosophers and physicists who have tried to make that idea precise, right? So I think when you're working with an FLRW model, it's going to be an approximation of some other model that's Heraclitus that's in the background, right? That's maybe really what our universe might be best represented as. But when you're studying things on such a grand scale, maybe those small little differences in curvature they're just not important for what for whatever you're studying. So it's just a matter of what you're looking at there. I don't think there's any contradiction or any tension there. You just have to keep track of what are we studying, what are we trying to model. And when you're trying to model something like FLRW, you're gonna naturally reach for spacetimes with all sorts of symmetries, because on a large enough scale there is going to be all sorts of symmetries. But of course, it's not going to accurately model our universe. I mean, we have clumps of galaxies here and not there, and so our universe is not completely symmetric, right? It's not completely homogeneous or isotropic.
Yes.
So all those assumptions are great if you understand what you're doing with those assumptions. As long as you're not banging your fist on the table saying, no, but this FLRW model, this really is an accurate representation of our universe, then there's no problem.
So if I had to bet money, I would bet money that if we're in a Heraclitus universe, that the curvature would average out to look like something like FLRW. But I know in effective field theories, there are precise theorems that show you that you can integrate out certain low-level details. I haven't encountered a Heraclitus spacetime until your work, so I don't know if it's the case that something like chaos would occur where something small actually gives rise to some large change when you try to, quote, integrate out into an FLRW or into these other approximations. Do you know or do you suspect it to be the case that if our universe is indeed Heraclitus, that wouldn't cause any tension with FLRW?
Yeah, I'm not aware. We're investigating some issues on the philosophical side of things. So we're investigating things like what philosophers have said for a long time about connections between, say, symmetry and structure and that sort of thing. So I haven't really looked at, what the implications are for this sort of thing for, something like quantum field theory. My guess is that you wouldn't run into problems. The examples that I know of that we've constructed, these are really simple models. It's not like they're pathological in any way. It's just that they are varied everywhere. It's not like there is any kind of curvature blowups. It's not like there's any even singularities anywhere. You can have globally hyperbolic Heraclitus spacetime. So I don't think it's messing anything up really. It's just sort of like a fine-grained kind of model of the universe that could potentially have implications for certain philosophical things that maybe some people aren't interested in them. But in philosophy of physics, for example, there is a long tradition of saying, well, the symmetries of an object tell you how much structure it has. If it's got tons of symmetries, it doesn't have very much structure. If it has few symmetries, it's got tons of structure. And so what we're doing with our Heraclitus stuff is kind of throwing a wrench into this and saying, well, at some point, you get to the stage where your asymmetries kind of max out. You can't be any more asymmetric than a Heraclitus spacetime, but your structure doesn't max out. You can still add on structure. You can still add on, a little sign that says, here's the center of the universe, or, so you can pile on structure, but that's not going to decrease the asymmetries. That's something that may not be of interest to folks, but in philosophy, this is decades and decades of folks writing about this, what we call dogma, this symmetry structure dogma, and we're trying to blow that up.
Hi, everyone. Hope you're enjoying today's episode. If you're hungry for deeper dives into physics, AI, consciousness, philosophy, along with my personal reflections, you'll find it all on my Substack. Subscribers get first access to new episodes, new posts as well, behind-the-scenes insights, and the chance to be a part of a thriving community of like-minded pilgrimers. By joining, you'll directly be supporting my work and helping keep these conversations at the cutting edge. So click the link on screen here, hit subscribe, and let's keep pushing the boundaries of knowledge together. Thank you and enjoy the show. Just so you know, if you're listening, it's CurtJaimungal.org, CurtJaimungal.org.